All right, last section, wrapping up our idea of Gibbs free energy and spontaneity. What's free about free energy? Free energy is the maximum amount of energy released from a system that is available to do work on the surroundings. So for many exothermic reactions, some of the heat released as a result of enthalpy change goes into increasing the entropy of the surroundings. So it is not available to do work, actually. Even some of this free energy is generally lost to heating up the surroundings. We desire for spontaneous reactions to produce useful work, right? We are always striving in our reality to do the maximum amount of work possible. Not all reactions are harnessed to do work, right? Heat loss is a real thing. I used to work for Southern California Edison back in the day, and I worked at a power plant. I was a chemistry project developer, and I made sure that the chemistry of the power plant was actually working soundly. It is very interesting. I worked at a natural gas power plant, but it's also called a combined cycle. So natural gas, we burned jet fuel, heated a turbine, spinned it around, created electricity, right? But the heat lost from that reaction actually was also used to boil water. The heat that was not being used to spin the turbine, but just going out into the atmosphere, we actually collected and used to heat up a boiler, which then boiled water to create steam, and then steam with higher pressures because the molecules are moving faster, they are bouncing around and they are creating pressure now, was actually pushed through another turbine to create even more electricity. So we were trying to harness the heat loss and create as much work as possible, as much electricity as possible. This is the goal of a lot of exothermic reactions, okay? So when we think about an exothermic reaction such as this one, carbon is reacted with hydrogen gas in an exothermic reaction to produce methane gas. This is similar to a combustion reaction, but combustion is specifically with oxygen gas. But that doesn't mean that we can't have a similar reaction with hydrogen gas. Now notice the delta H of the reaction is negative 74.6 kilojoules per mole. It's exothermic. Delta S, we are negative here, negative 80.8 joules per Kelvin because we are unfavorable. We are creating three molecules forming into one, right? We're getting more structured. The delta G of the reaction is negative 50.5 kilojoules. And that is less than delta H because some of the heat released or some of the energy released is heat lost to the increase of entropy to the surroundings. All right, so it's not a perfect enthalpy to Gibbs free energy. There is some heat loss, and if we can harness heat loss in science, then we can actually find a reaction that is real, a real reaction. Real reactions. In a real reaction, some, if not most, of the free energy is lost as heat. That can be seen as batteries making a motor turn, right? The motor is using the actual current, the battery itself, to spin or to do whatever it's supposed to do to produce work, right? Mechanical work. Think about mechanical work, right? Same idea as spinning a turbine. But as that motor is spinning and going back to the battery, the current going back to the battery, there is heat lost from all of these movements. There is a decrease in the potential of work. Therefore, real reactions are technically irreversible. Now, when we want to think about calculating the maximum amount of work available is just another way of talking about Gibbs free energy. However, when delta G is 0, I want to just take a moment to talk about equilibrium before we get to the equilibrium chapter. An equilibrium reaction is one in which it is reversible. The free energy of the reactants and the products are always going back and forth, remaining spontaneous forward and spontaneous backwards. Notice here the equilibrium mixture is the lowest free energy possible. And so what we're going to be able to say is the G of the products is equal to the G of the reactants. And that's how we get the change in G of the reaction to be 0. We see this for weak acids. When we talked about weak acids last semester, we said that they were not good at ionizing in water. They can, but they are not good at it. They don't mind going back. So they can ionize in water, but they also can go back to be the weak acid form. Many reactions do this. Many reactions are going to be in an equilibrium. Let's dive into one more type of equilibrium. H2O solid and H2O liquid. At the actual phase change, we are technically at a dynamic equilibrium. At 0 degrees Celsius, there is the ability to be a liquid and a solid, right? Above 0 degrees Celsius, water exists as a liquid. Below 0 degrees Celsius, water exists as a solid. At exactly 0 degrees, a liquid-solid mixture exists. So at equilibrium, that is this specific setup, right? The equilibrium exists at 0 degrees Celsius. We can also calculate at which temperature equilibrium will occur, okay? So utilizing delta G is equal to delta H minus T delta S, if we looked up this specific reaction for its enthalpy and entropy, we could say at 0 for delta G, at equilibrium, what is the melting point, right? And so what that would be is if we were to rearrange this, T delta S is equal to delta H, temperature at the phase change. How do we actually calculate the temperature of phase changes? It's by taking the enthalpy and dividing it by the entropy. That's pretty trippy, huh? That's pretty crazy. And so looking at enthalpy and entropy, it's really, really important to be able to do a little bit of delta G work at equilibrium. These are interesting positions. The specific one that we're showing here is actual phase changes. There will be a lot more reactions at equilibrium when we get into chapter 15.